That's doable when by hand plugging it into the formula won't be doable. So here's our example. Two legs of a right triangle are measured as 5 meters and 12 meters. But you could be off. The instrument that you're measuring with, maybe it's not calibrated correctly, so it could be off by as much as 1/5 of a centimeter, 0.2 centimeters, plus or minus, in both the measurements. For the 5 meters and the 12 meters, you could be off by that amount. Possible error on one of them and on the other one. On the 5 is 1/5. Possible error on the 12 is 1/5. You're possibly off by 1/5 in each measurement. So then the question is, okay, if you're off by that amount in each of those measurements, then if you want to go calculate a formula that involves those variables, then what does that cause you to be off? First off, we're going to calculate the area of the triangle. And then we're going to calculate the length of the hypotenuse and find out how much off we could be. So in general, it's a right triangle. It's not a special. It's not a generic triangle. It's a special triangle. So one leg is 5, the other leg is 12. Pythagorean triple, we know the hypotenuse should be 13. Okay, great. So that's for part B. We should get something very, very close to 13 for part B. But for part A, it's the area. For a right triangle, what's nice is that the area is just the product of the legs, and then you have to divide by 2. So the area of this triangle is just 30. Okay? But if we're off by 1/5 of a centimeter, our increment in x or y, if you want to say it that way, if we're off by 1/5 of a centimeter, what does that cause the area to be off by? And so we need a formula. Our formula is going to be that in such a triangle, the area is just 1/2 the base times the height, so 1/2 of xy is our area. This is our multivariable function z, function of x and y. And so we're going to take the partial derivatives, and we're going to find out how z can change, how this area could change. When I change x by 1/5 of a centimeter, when I change y by 1/5 of a centimeter, the question is, how does area change? And so that's absolute value plus or minus, so we can just go with the absolute value. And we say, okay, the partial derivative with respect to x is half of y. The partial derivative with respect to y is half of x. What do we do with these guys? We multiply them by the change in x and the change in y. But be careful, there's issues here, of course. In most of these problems, with this small increments, they end up causing issues when they do watch this units here. We have to make an agreement as to what unit we want to be in. Okay, we can't just say 0.2 because 0.2 is of a centimeter, 1/5 of a centimeter, and then the original units are in meters. So we just make some agreement to make a match. Make everything centimeters or make everything meters. They just have to agree. So be on the lookout for these types of problems because the sort of small change is usually done by also changing the units as well. So instead of saying, off by, 0.002 of a meter, we say 0.2 of a centimeter. And so these units don't match. So we make everything the same. The delta x is the dx. That's the maximum error in x and the maximum error in y. And we say, let's go everything in terms of meters. So we say 0.002 of a meter. Right? Yes, it's 1/5 of a centimeter, but it's 1/500th of a meter is how we want to make them match up. Same thing for y. And so this is what we're going to multiply our a sub x and our a sub y. Our partial derivatives here will get multiplied by the associated dx and dy. In this case, they're the same, though, because the instrument that you're using could be off by that amount. So when you didn't make these two separate measurements, they could be off by that amount. And so we go calculate. We take half of 5 and multiply by 1/500. We take half of 12 and multiply by 1/500. And that'll be how much area is off by. This is our differential in area. It'll give us the change in area. We know the area should be 30. Okay, we're not trying to approximate area. What we're trying to do is figure out how much area is going to change by. Okay, and so plugging this in, we end up with 0.005 and 0.012. So area is should only change by 0.017 of a square meter. So if it's 30 meters squared, then by you being off, by your instrument not being calibrated correctly by this very, very small amount, it seems like it causes this much for your area to be off by. But a better measurement that we want is percentage error. Okay, this is the maximum error in the calculated value. At most, if you're going to use this measurement tool, which isn't calibrated correctly, you should be willing to accept that your error is going to be this much. This is your tolerance based off of your calibrated instrument that isn't calibrated correctly. But percentage error is what you really want. Relative error. In the big scheme of things, that's so small of an amount. Because your area is 30 square meters, and so with respect to that 30, this is the actual, right? The 30. So you divide by the 30 to figure out what percentage that is. Percentage error or relative error is a better measurement. Now, you can't do this without a calculator, but I just want you to see how small a percentage off this is, and then you just have to decide, whether you're willing to accept this or not. And so, if this is in your tolerance, then you say, then we don't have to recalibrate that measurement tool. We'll continue measuring things with this tool, although it is off by this small amount for the quality control if you're in this business or whatever. Okay. Questions on this whole process? And behind the scenes, we're really just using a tangent plane. We're making a function. We're finding the tangent plane approximation, and we're just plugging in the change in x and change in y. The length of the hypotenuse should be 13. We're going to find out that we're going to be off by using the Pythagorean theorem. X squared plus y squared should be z squared, or z is the square root of that. And we're going to get a different kind of error, relatively speaking. And so, take the partials. This is now my multivariable function. I had this guy before, now I have this guy. Take my partials and still multiply by the same dx and dy, though. The partial derivatives are just 1 over 2 of those same square roots times 2x or 2y. So your 2's cancel out. You get those partials. And you multiply them by 1 over 500, essentially. Or 2 over 1,000 if you want to write it that way. So with 5 and 12 plugged in, we know the root becomes 13. So we're talking about 12 thirteenths times the 1 over 500 and 5 thirteenths times the 1 over 500. Okay. And that'll give me my change in z, my approximation to the change in z. Okay. I mean, it's possible without a calculator. It's not the best thing to do, but you get 0.0026. Relatively speaking, though, I mean, size-wise, but the units are different. But size-wise, this is very, very different. And so, it gives us a different relative error. Sorry. Because the number should have been 13, so relative to 13, this number here is bigger, as opposed to being this guy relative to 30. And so maybe you're not willing to accept, it depends on, what your tolerance is, but, for this measurement, we get still less than 1%, but maybe we're not willing to accept. It's a different relative error based on the size. It's all about size. And so if we're trying to calculate something with a bigger number, maybe this is microscopic, but with a smaller number like 13, maybe this isn't something that I'm willing to accept being off by that much. Okay? I mean, without a calculator, I don't know what I could really, we could set it up at least. This is a tough calculation to do without a calculator. It's doable, but we have to make better the numbers have to come out better, I think, if I was going to ask this on an exam, or if you see some of the My Math Lab or the hand-in questions. But I just want you to see the process. Questions on the process.